Hello. So, in this lecture, we will continue our discussion of hydrostatics. So, in the previous lectures, we looked at the derivation for the the famous equation P is equal to rho g h, where h is the depth below the fluid surface or the liquid surface in general, because we experience the hydrostatic force more commonly in liquid, because that is where it is predominant, but we also experience it in gases. So, P is equal to rho g h first we looked at, and in the next lecture we looked at the forces on a surface which is submerged in a fluid. Now, this surface can be a plane surface or a curved surface. So, we looked at that what is the magnitude of this force and at what point will it act. Okay. So, we looked at the force, its magnitude for a plane surface, and we looked at what will be the magnitude of various components of the forces. We discussed it in terms of horizontal force, horizontal components of the force and the vertical component of force, and we saw that for a curved surface, if we take a projected area on the plane, we can treat the analysis as for a plane surface. Okay. So, now what we are going to look at buoyancy in today's lecture, and once we have discussed buoyancy, we will take up few examples for the submerged surfaces as well as one example for buoyancy. Okay. So, all of us have been hearing about buoyancy or have been reading about buoyancy for a number of years, since our school days, class 8th or 9th, the concept is introduced to us. What is buoyancy? We know it better as Archimedes principle. So, which says that a body when submerged partially or fully in a liquid, the body experiences an upward buoyant force on it, and this force is equal to the weight of the fluid that the body displays, and the principle is known as Archimedes principle. So, Archimedes was a Greek mathematician, physicist, engineer, inventor and astronomer. So, he did a number of things, or he developed a number of concepts in mathematics, and the most famous work of Archimedes is what we know as Archimedes principle, and that is about buoyancy. So, a story goes like this, that the king of Syracuse, he asked Archimedes, the place where Archimedes used to live, he asked Archimedes to find if a crown that he has ordered for a temple to a jeweler, and he suspected, he gave pure gold to the jeweler, and the king suspected that there has been some amount of other metals mixed with the gold. So, he asked Archimedes to find out if the crown is made up of pure gold. So, the way Archimedes wanted to find its purity was by looking at the density. So, he could measure the weight of the crown, but because the crown is of irregular shape, so the question he asked himself was how I can measure the volume of this. And he was thinking about it. So, one day he entered in the bathtub to take bath, and he realized that when he enters in the bathtub, the volume of water or the level of water goes up. So, then he thought that okay, this is an excellent method by which I can find the volume of a body of an irregular shape. So, he then submerged the crown in the tub and then obtained the volume. Okay. So, that is the story, but then this work has been published in journals about the buoyancy force. So, basically it says that the force that a body when it is submerged in a liquid is equal to the weight of the fluid that the volume of the body that is submerged displaces. Okay. So, now we having known the principle of hydrostatic, we will try to see or try to derive Archimedes principle from what we have studied, and we will do it to different methods here. Okay. So, let us look at a let us say that in a fluid or in a liquid, the blue colored rectangle, you consider it as liquid, and in this a body is submerged. Now, we can divide this body into two curved surfaces. One, we can say the upper curved surface and the other one, let us color it in a different one. So, this can be divided into upper curved surface. Now, from the previous lectures we know that the vertical force on this submerged surface, the upper curved surface, will be equal to the weight of liquid that is above the surface. So, the vertical force on this surface will be acting downwards and will be equal to the weight of the liquid. Let us just hatch this volume by the horizontal lines. Okay. So, the volume of liquid that is above this curved surface pointing downwards will be the force on this curved surface. Now, if we take the lower curved surface, then what is the vertical force on this lower curved surface? So, by seeing this we know that the force on this curved surface will be acting upward. So, it will be opposite to what is opposite to the direction on the upper surface. Now, the magnitude of this force will be equal to negative of this. So, it will be, if we say that the force is positive in the vertically downward direction, then this will be negative force, and it will be equal to the weight of the liquid that is above this surface. So, it will be equal and opposite in direction to the weight of the liquid that is above this surface. So, this is the net force on the lower surface. So, if we combine the two, that the net vertical force on the body caused by the fluid will be the net vertical force on these two surfaces, which make the surface of the body. So, that will be equal to the weight of the liquid above the surface minus weight of the liquid above the upper surface minus weight of the liquid above the lower surface. So, that will be equal to the weight of the liquid equal to the volume of the body, and that will be acting upward. If we follow the sign from here, that will be a negative sign. So, weight of the liquid equal to the volume of the body, that will be the force and it will be acting upward, and that is what Archimedes principle is. So, by simply looking at the force on the entire surface of the body, the hydrostatic force acting on the entire surface of the body, we could obtain Archimedes principle. Now, we will do the same exercise, but in a slightly different manner. So, if you again take the body and take a element, a slice having a area d a, and you take 2 points on this body or a small slice, point 1 and point 2 on the upper and lower surfaces of this body. Then, so the force on the lower surface will be P naught plus rho g h 2, where h 2 is this depth, and h 1 is the depth of point 1. The force at point 1 will be P naught plus rho g h 1. So, if we say that the z direction or the positive direction is pointing upward, then the net force on the element is P naught plus rho g h 2 d a, which is acting upward, minus P naught plus rho g h 1 d a, which is pointing downward. So, the net force on this will be P naught and P naught will cancel out because area is same. So, what you have is rho g h 2 minus h 1 d a, and that will be acting upward. Now, h 2 minus h 1 into d a is nothing but the volume of this body of this small rectangular body. So, h 2 minus h 1 is the height and d a is the cross sectional area. So, that will be equal to rho g, the volume of this body, and so the force in this body is the integral of rho g d v. Okay. So, we will use V strike through for volume, because we also use V for velocity. So, in order not to confuse ourselves, we will try to use V strike through as a symbol for volume. So, here V strike through is the volume of the body. So, again rho is, remember, it is density of the fluid, not that of the body. Okay. So, again the force on the body is equal to the weight of the fluid that is equal to the volume of the body. So, again we have been able to derive Archimedes principle. So, now in hindsight we see that Archimedes principle is nothing but a extension of the principle of hydrostatics, that P is equal to rho g h at a particular depth h in a fluid. Okay. So, now we will look at a problem. So, let us read the statement of the problem, that there is a cuboidal tank and this tank is filled with 3 different fluids having densities rho 1, rho 2 and rho 3, and rho 3 which is filled at the bottom has the highest value, and then it is greater than rho 2 and rho 2 is greater than rho 1. The height of these fluids is same h for each, and the bottom of tank is square shape. So, the dimension, this dimension is d, and the dimension normal to the screen or perpendicular to the screen is also d. We can assume that the pressure outside above the liquid surface is P naught and outside is P naught. So, when we consider hydrostatic pressure, if we write P naught plus rho g h, so from the other side of the surface we will again experience pressure of P naught. So, we will consider only the hydrostatic pressure caused by the liquid column while solving this problem. Okay. So, the questions are that we need to find the hydrostatic force on a side wall of the tank. So, the tank is cuboid shape and it has square cross section. So, the area of all the side walls will be same, it will have 4 side walls, and the question asks us to find the hydrostatic force on any of the side wall of the tank. Then the next question is, we need to also find the point of action of this force on the side wall, and the third question is, what is the hydrostatic force on the bottom wall of the tank or on the bottom of the tank. Okay. So, let us look at the first part, that the hydrostatic force on the side wall of a tank. Now, we see here that the density is different in the 3 fluids, rho 1, rho 2 and rho 3. So, we cannot directly use our relationship that we derived, that P is equal to rho g h at the centroid for a column of liquid. It is not varying continuously. So, we can divide it into 3 different liquid columns, or we can treat these as 3 different liquid columns and obtain the net force on the side wall. So, that is what we will do, that the side force in the first liquid column at the top will be acting on the centroid of this liquid column. So, that will be H C 1, which is equal to H by 2. So, remember that this is not the point of action of this force, it is just to find the magnitude of force. We can find that P, because of the first column, is rho g H C 1. H C 1 is the centroid. So, rho 1 g H C 1 for the first column. Similarly, for the second liquid column, H C 2, if this is H C 2. So, the pressure will be rho 2 g H C 2. So, rho 2 g H C 2 will be equal to h, which is the height above, plus h by 2. So, h C 2 will be equal to three by 2 of h, and the force on the bottom column will be the pressure rho 3 G H C 3 into the area of that particular the wall that is in touch with this column. So, H C 3 will be equal to H plus H plus H by 2. So, that will be equal to 5 H by 2. Okay. And the area for each case will be, because the height or depth of the column is h multiplied by the dimension normal to the screen, that will be the area. So, h d. So, we can substitute those values here, and we see that for the first column the force will be rho 1 g h by 2 into h d. For the second column rho 2 g 3 h by 2 into h d. For the third column rho 3 g 5 h by 2 into h d. And we can take g h by 2 out of the bracket. So, we will have rho 1 plus 3 rho 2 plus 5 rho 3 into h square by 2 d g. Now, if we simplify this, that rho 1 is equal to rho 2 is equal to rho 3, then what will we have equal to 9 rho h squared by 2 g d. Okay. So, 9 by 2 is 4.5, which will be the centroid of this. Okay. So, that will be the net force on the side wall of a tank. Now, the next question is the point of action of force on the side wall. So, the point of action of this force on the side wall we can obtain by taking the moment, let us say on this point, about this point O, and we can assume that the general depth is y from the top of this column. So, we can have we can write the moment equation that for the resultant force F side into y dash. So, y dash is the depth below the liquid level at which the force will act. Of course, in the direction normal to the screen, this will be symmetric. So, it will be at the middle of the surface. What we need to find is only y dash. So, F side into y dash is equal to, for the first column we will have y into d f or p d a. So, y is the distance for a small, if we take a elemental volume. So, y into rho 1 g y, which is the pressure, into d, d is the side normal to the screen, into d y is the small or the height of this depth of this elemental volume. So, this becomes d dy is basically d a. Similarly, we will have for the second column where rho 1 will be replaced by rho 2, and for the third column rho 2 will be replaced by rho 3. And the integration limits for the first column from 0 to h, for the second column h to 2 h, and for the third column 2 h to 3 h. So, when we do this integration, for the first part we will have rho 1 g d, which are all constant, y squared dy. So, when you integrate y squared dy, you will get y cube by 3, and if we substitute the limits from 0 to h. So, h cube by 3 minus 0. So, from the first term we get rho 1 g d h cube by 3. From the second term, similarly we will get rho 2 g d 2 h cube by 3 minus h cube by 3, and for the third term rho 3 g d 3 h cubed by 3 minus 2 h cubed by 3. Okay. So, let us simplify. First term will be same, this next term will be rho 2 g d 7 h cube by 3, and the third term will be rho 3 g d 19 h cube by 3. We can further simplify and substitute the value of the net force, so that we obtained just few minutes back. So, y dash is equal to rho 1 plus 7 rho 2 plus 19 rho 3 into h cube by 3 g d divided by rho 1 plus 3 rho 2 plus 5 rho 3 into h squared by 2 g d. So, that is our y dash. We can cancel out g d by g d and h squared. So, we will get 2 by 3 h into rho 1 plus 7 rho 2 plus 19 rho 3 divided by rho 1 plus 3 rho 2 plus 5 rho 3. Okay. So, that is the location of the line of action of this force, which will be at 2 h by 3 into this whole expression in terms of the densities of the fluids. Okay. So, now the third part is simple, that what we need to find is the hydrostatic force on the bottom of the tank, which will be equal to the weight of the fluid or fluids above this tank. So, that will be the weight of the entire fluid column. So, rho 1 g h plus rho 2 g h plus rho 3 g h multiplied by the area of the bottom, which will be d into d. So, d squared. Okay. So, if we take g h out from the bracket, we will get rho 1 plus rho 2 plus rho 3 within the bracket multiplied by g h d squared. Okay. So, in this we have a assumption that the heaviest fluid, which is rho 3, is at the bottom, and then the next heavier fluid, and then the lightest fluid rho 1 at the top. Now, that is of course obvious that if we do not have such an arrangement, what will happen if the fluid at the top is heavier than the fluid at the bottom. So, if rho 1 is greater than rho 2, what will happen, that the liquid will start or the heavier liquid will start coming down, and the lower liquid or the lighter liquid at the bottom will start going up, and this will give rise to an instability. So, one of the common examples which we can experience, or we can do experiments also, you can take two glasses of liquid, one filled with water and another having a liquid of lower density. So, for example, you can take an oil which has a density lighter than oil, you can fill lighter than that of water. You can fill both the glasses, put a some surface, solid surface or plain surface or a paper on the top of oil, turn up the water on it, and then slowly remove the separation, which is a paper or metal sheet or whatever you have, and you will realize, or you will see that the fluid, if they are immiscible, then the oil will start coming up and the water will start coming down, because water is heavier than the oil. And this is this phenomena is known as Rayleigh-Taylor instability. So, the instability is a common name when you see that the instability refers that if you disturb a system in equilibrium, or if you give a small perturbation to the system, and if this perturbation grows continuously with time, then the system becomes unstable. So, such phenomena are known as instability, and there are a number of fluid instabilities or number of instabilities that occur in fluid mechanics. So, the name this phenomena is given the name as Rayleigh-Taylor instability. Okay. So, this is just because we are talking about the fluids of different densities on one above the other. So, I thought I will introduce the term to you. There is whole lot of mathematical description based around it, because this has application in a number of areas, especially in atmospheric fluid mechanics or fluid dynamics. The system of course will not remain static anymore, because the fluids will start moving. Okay. Now, we will look at the force on a curved surface problem. So, what this talks about, that there is a glass observation room that is to be installed at the corner of the bottom of an aquarium. So, if you go and visit an aquarium, some of the aquariums have which are close to sea, there you can see the fish, especially the bigger fishes such as dolphins from the bottom, and you can see from them from a glass enclosure. So, let us say that the problem talks about having a so, it says that there is a glass enclosure, and let us say that this glass enclosure is somewhere here, okay, and we can just hatch this surface, so that it is easily identified. Okay. So, this will be a 1/8 part of a spherical cell. So, you assume a hollow sphere and cut from 3 planes. So, what you will have is 1/8 of an sphere. So, the aquarium is it has at the corner of the bottom a observation room, which is a spherical cell of radius r. So, the radius of this spherical cell is r. Height of this aquarium is given to be h. Okay. This is symmetrically placed in the corner. So, that is why it will have 1/8 of a sphere. You can assume the density of the water or sea water to be rho, and the pressure at the surface of the liquid and pressure inside the observation room to be same. So, the pressure here is P naught, and pressure on the other side of the observation room where there is air is also P naught. So, we do not need to consider the pressure in our analysis or P naught in our analysis. Now, what we need to find is the resultant force on the glass surface. So, we can have this glass surface, of course, will have 3 projections in all 3 directions on the 2 side walls and the bottom wall. So, we can have a force on the one horizontal surface and another horizontal surface. So, let us say that these are x and y surfaces which are normal to each other. So, the direction will be once in the x direction the force will be acting and the other force will be acting in the y direction, but their magnitude will be same because the projections on it is placed, the glass surface is placed symmetrically. So, the area projected on x surface and area projected on the y surface, they will be equal. If we are able to obtain the force in the x direction, we will be also the magnitude of force in the y direction will be same. The third surface or third area projected will be vertically downward or the bottom surface. We can obtain the forces. So, let us see the f x and f y, they will be equal to pressure into the area. So, the area of this glass surface will be 1/2 of the cross section of. So, pi r squared will be the, if we cut the sphere in the middle, the area will be pi r squared, but the projection will be only 1/4 of it. So, the area will be pi by 4 r squared. Now, the pressure will be rho g h c, where h c is the centroid, and from our knowledge of mechanics, we can find or we can look into the books that for a semicircular surface, the centroid is located at 4 r by 3 pi from the center. So, the distance of the centroid from the top surface will be h, which is the depth of the liquid or the distance from the liquid label to the center, minus the location of the centroid. So, 4 r by 3 pi. So, h minus 4 r by 3 pi is h c. So, that will be the force in x and y direction, and the force in z direction will be equal to the weight of the liquid above this liquid column. Now, the liquid column will have, so at the bottom it is circular. So, if we look at the liquid column, that will be part of a one-fourth of a cylinder of radius r and height h. So, the volume of the cylinder or volume of liquid in this cylinder will be pi by 4 r squared h, which is cylinder volume divided by 4, and we will have to subtract the volume of this sphere. So, sphere volume is 4 by 3 pi r cube, and it is only 1/4 of the 1/8 of the sphere. So, 1 by 8 of 4 pi r cube. So, when we multiply it with rho g, that will give us f z. Okay. So, we have obtained the 3 components, and that is what has been asked. Okay. So, let us look at the next problem, which is about buoyancy. So, it says that hydrogen bubbles are used to visualize flow streak lines. A typical hydrogen bubble has diameter of 50 microns, and the hydrogen bubbles rise slowly because of buoyancy and attain a terminal speed. What we need to find is the buoyancy force acting on the bubbles immersed in water, and we also need to find the terminal speed of a bubble rising in water if the drag on the force is this. So, when we need to measure the velocity, and one of the common techniques to measure velocity to introduce tracers in the fluid, and these tracers should be such that they can follow the fluid faithfully. So, the hydrogen bubble talked about in this example is one such tracer, that it is very small in diameter and it will quickly relax or its velocity will be equal to the fluid velocity within no time. Okay. The Stokes flow generally refers to the flow when the Reynolds number is very small. So, when the fluid velocity is very small, the length scale in this case the bubble diameter is very small. So, the Reynolds number is sufficiently lower than 1, then we can call the flow as Stokes flow. We will discuss it later on, and you would have studied in your school that the drag force on a bubble rising or a liquid dropping in a stationary fluid or a quiescent fluid is 3 pi mu v into d, where v is the velocity or the terminal velocity, because when a bubble rises, it will start rising with a velocity and then because of the drag experienced by the bubble, the velocity will slow down, and finally the two forces, the buoyancy force and the drag force. Of course, there will be some mass, but that can be negligible when compared with the buoyancy force. So, when all the forces on the bubble, they are in equilibrium, it will have 0 acceleration and it will achieve a constant velocity, and that velocity is what we call terminal velocity. So, the first question it asks that what is the buoyancy force acting on this bubble. So, that is simple. Buoyancy force will be weight of the water displaced by this bubble. So, the volume of this bubble will be pi by 6 d cube, which is where d is the diameter of the bubble, and multiplied by rho w density of water into gravity. So, that will be weight of the water displaced by the bubble, and that will be equal to the buoyancy force. The forces acting on this will be the buoyancy force, the drag force, which will be opposite in the direction of opposite to the direction of motion of bubble, and some mass of the bubble. So, the bubble will achieve a terminal velocity if these forces are equal, because we can neglect this, because rho of bubble or rho of hydrogen is very small when you compare that of water, about 3 order of magnitude small. So, we can neglect that, and if we substitute the value of f d, which has been given 3 pi mu v d, and substitute the value of f b buoyancy force, which we have just calculated, rho w g pi by 6 d cube, and by cancelling out the terms. So, pi will cancel out and d will cancel out. So, you will have d squared here. So, you will get v is equal to rho w g d squared by 18 mu. Okay. So, that is the terminal velocity of the bubble. Okay. So, with that we come to the end of this lecture. In the next lecture, we will look at surface tension and related concepts. Thank you.